So good afternoon, and thank you for the opportunity to presenting VTT's activities related to quantum within photonics. And I would like to start with a brief overview of VTT's activities that is about low-loss platforms. So in VTT, we develop two different low-loss platforms, one based on silicon nitride and the other based on thick silicon on insulator, which is with the thickness of silicon of 3 micrometer. So I'll start with the silicon nitride platform. We are currently developing this platform with the current loss estimate of 0.5 dB per centimeter. But still work is in progress, so we would like to reach even lower propagation losses within this platform. And we also have a mature thick soy platform developed with the ultra low loss of 4 dB per meter propagation loss, which is built based on 3 micrometer thick silicon on insulating layer. So a brief introduction about the silicon nitride platform and the components, passive and active components at VTT we are developing. We are targeting applications within quantum sensing and quantum communication using this platform. Our current waveguide design covers wavelengths range of 900 nanometer to 1600 nanometer. These silicon nitride waveguides are thermally more stable, provide thermally more stable platform compared to silicon waveguides because of the lower thermo-optical properties of the silicon nitride. And on the other hand, we can also integrate like monitor temperature sensor as a ring resonator on the chip to monitor in situ temperature for the different integrated within different chips built on silicon nitride platform. On the other hand, it can be used as an evaluation platform for graphene photodetectors and modulators. We developed a wafer scale graphene photodetector fabrications with the with the detector responsivity with no bias of 1.8 milliamp per watt, and with the bias of 100 millivolt, we can reach responsivity of 700 milliamp per watt for these graphene detectors. So this can have applications as the fast detectors integrated within different quantum photonics platforms. So the other platform we developed is a thick soy platform. VTT's thick soy platform provides the possibilities for both hybrid and monolithic integration of active and passive components. We can benefit from ultra low loss properties within this platform. Because of the thicker dimension of the waveguide, we have good mode confinement and less effect from the wall roughness and waveguide wall quality fabrication on the propagation loss. So here are the different components and a sketch of different components we developed at VTT with the current performance of the waveguide and mirrors, detectors, and Euler bands. So this platform brings a unique opportunity and building blocks because of the very low propagation loss below 4 dB per meter and fast and responsive integration of detectors, and at the same time integrating of reflecting mirrors for broadband and polarization independent coupling to the different platforms integrated through, let's say, flip chip bonding or other techniques to our thick soy platform. So I will give a brief example of one active component, germanium detectors we integrated on our platform. So monolithically integrated germanium detectors developed for quantum communication and quantum key distribution applications mostly, which are targeting high key rate and larger scale deployment. This platform includes monolithically integrated germanium photodiodes, responsivity in the range of 1 ampere per watt at telecom wavelengths. So we developed both high-speed PDs and monitor PDs, high speed with 40 gigahertz when operated with 1 volt reverse bias and dark current of 4 microamp, and also lower speed with 1 gigahertz speed and dark current of 10 nanoamp at the moment. This is the performance of our detectors. And we are also doing cryogenic characterization of the performance of these detectors to figure out how they function at low temperatures. There is one use case application of this monolithically integrated germanium detectors for continuous variable QKD applications. We are developing balanced detectors on our TICSOI waveguide to be integrated within Lux Quanta's continuous variable QKD receivers. This use case is defined within QPilot project, which is a Horizon Europe project to establish pilot line services within Europe. Integrating balanced detectors, including hybrid 90 optics, is very important to get lower loss and better performance for these monolithically integrated receivers for CVQKD applications. Also, our in-house expertise in developing ultra-fast electronics and transimpedance amplifier design are used to reach the performance, the design performance in the range of 1 gigahertz speed for this in these balanced configurations. So integrating this with low loss hybrid 90 also gives better relative phase and time jitter compared to balanced detectors based on optical fibers, and in general it can be helpful to improve overall performance of the QKD systems. Other type of detectors, we are working on our superconducting nanowire single photon detector SNSPDs, mostly for DV discrete valuable QKD applications. SNSPDs are used to, as you know, to receive quantum signals transmitted using, in this case, DV QKD protocol. Implementing in this central node configuration, we can do hybrid SNSPD integration on our SOI platform using high precision Philip chip bonding. Here is a 3D sketch. Our solution for Philip chip bonding of arrays of SNSPDs within our low loss within our low loss silicon uninsulating platform, which gives also higher fabrication yield to do this integration in 2 different platforms. We can run in parallel fabrication run for the waveguide part and also fabrication for the SNSPDs. And then at the end, using Philip chip bonding and especially benefiting from a polarization independent upreflecting mirror, we can bond these 2 chips together and couple single photons or Gaussian states to arrays of SNSPDs. And also we developed array to waveguide gratings to demultiplex WDM signals coming from single fiber and couple them to SNSPD arrays. In this hybrid approach, this is part of a Cryocom project, and we got test SNSPD arrays from single quantum, and we integrated it within our TICSOI platform. Also, in parallel, we are developing our own SNSPD fab runs. We have a niobium nitride SNSPD fabrication, and also we are developing a wafer scale process for amorphous superconducting molybdenum silicide in our co-sputtering, using co-sputtering techniques. Mostly deposition is developed and different ion bombardment techniques like gallium and argon has been tested on it to test the amorphization effect of different ions to lower to improve the superconducting transition temperature and the superconductivity performance of these MOSI films on a wafer scale. And this is still work in progress, and we are collaborating as part of different projects to improve these fab runs. And as the final note, I would like to take also the opportunity I mentioned that VTT is coordinating a quantum pilot line project in collaboration with several RTOs across Europe, TNO, IMEC, Fraunhofer, CIE, and several other pilot lines that you can see in the figure here. So the goal is to develop a sustainable ecosystem to provide pilot line services for European companies, startups, and SMEs active in the field of quantum. We also part of the QTest project. So the idea of these two projects is to develop fabrication pilot line and also test line for quantum technologies across Europe. So within these projects, we are launching open calls, which is interested for European companies, SMEs, startups. So we highly encourage European companies to keep in touch with us and check our webpage. So the call will be launched in June. And within this call, we will get several use cases depending on the needs from different companies. We have the technologies to be offered. You can find them in the webpage. And within this project, all the companies will get, selected companies will get 100% subsidized services from the pilot lines involved in the QPilot and QTest project. And specifically, we have Photonics platform for quantum technologies, which would be very interesting for the European companies active in the field of quantum photonics. Thank you so much for your attention. It was all from my side about VTT's activities.